Hi everyone, welcome back to my channel. My name is Chacha, and today I'm going to be going over Sn1 and Sn2 reactions in organic chemistry. This and functional groups, in my opinion, are the most important concepts that you'll encounter on the organic chemistry section in the MCAT when you're reading the Kaplan books or just studying for the test in general, just because I feel like a lot of the later and more complex reactions and just other mechanisms that you'll learn about, they heavily build upon this and also E1 and E2, but those aren't really reaction or core principles that you really need to know for the MCAT, or at least they're not in the Kaplan books, which is what I use to help me study for content. First, let's go over Sn1, which is often referred to as a two-step mechanism, which can be a little confusing because it is Sn1, not Sn2. Even though there's two steps, whereas Sn2 is a one-step or also known as a concerted mechanism. So I want to break down the steps for you real quick. So you have your tertiary substituted substrates with your three R groups, which are your other carbon chains. You have a leaving group, then you can form that carbocation formation. And that's step one. Really, it's really important to keep in mind that this carbocation is sp2, or at least in this case for tertiary, it's sp2 hybridized. That's important for later. And step two, you have a nucleophile that comes in, attacks that positively charged carbocation, donates both of its electrons, which is a coordinate covalent bond. Remember, when the nucleophile donates both of its electrons, or anything just donates both of its electrons, that's a coordinate covalent bond. But after that bond is formed, it just reacts like a regular covalent bond where the electrons are shared between the two atoms, oftentimes disproportionately, depending on how electronegative your two atoms are relative to the other. Okay, so why am I saying that the sp2 hybridization of that carbocation is important? Because it's 50-50 stereochemistry. Woohoo! So what do I mean by that and why? So basically that means it's because it's sp2 hybridized, it can attack from the front, which I have here. So imagine that you have, or the back. So the front, imagine you have, let's say that this leaving group, for whatever reason, was a wedge. Okay, never mind. It doesn't like me. Was a wedge. Okay, so if you attack from the front, you're also going to have a wedge. But if you attack from the back or backside attack, which is fun because it rhymes, then it's going to be transformed into a dash. It's just as how it works. Um, Also another thing to keep in mind, because it is this two-step reaction, right? Then that means that there's two rates that you have to keep in mind. But when you're considering rate laws, only the rate limiting step or the slow step is what is important. And typically the rate limiting step is when you are forming something that is more unfavorable. So looking at this, typically how you could, right off the bat, how you can clock what is unfavorable is when you have something that has charge. In this case, the carbocation formation has a positive charge. The universe does not like stuff to have positive or negative charges just because it's unstable. It's highly, highly reactive. So that means that you don't want to form it. To have this leaving group go away, it needs a lot of effort. It needs a lot of enticement in order to do so, if you will. Um, so there's a lot of different ways that you can make this happen that makes it more enticing for that leaving group to go away, which is why the Sn1 reaction is it can be picky. It can pick and choose because it has every right to do so just because it's unfavorable and and the universe doesn't want to explode. Um, so, oh, and then there's also the formation of the nucleophile to that substituted carbocation. And this is a fast step because remember that nucleophile is creating the substrate to have a net zero charge. So that's highly favorable going from a positively charged state to a neutrally charged state. Um, yeah. And then, so what are some of the ways that you can make this more reactive, the to increase the rate of the leaving group? Um, for first tertiary substituted substrates, remember, if you have something that has carbon, carbon can donate some of its electrons to that carbocation up here. And that can make it more favorable. Whereas if you, let's say, for example, that this R here, for whatever reason, it is fluorine. Okay, remember, fluorine highly, highly electronegative. Electronegative in this state, when you have a positive charge, not great, right? Since what does electronegative mean? It means that this fluorine is going to hoard all of the electrons towards itself. It's a very, very greedy atom. And when something is greedy, then that means that this positive charge, it seems more positive because it doesn't have any electrons to help alleviate it. So it's going to be a more positively charged state, making it more unstable. So that's not good. You want to have stuff that is a low electronegativity, just like carbon, since carbon is the same, is equal to it. And it can donate some of its electrons, making this negative charge kind of like decrease. But it's still positively, sorry, not negative. This positive charge increase in how powerful it is, but it's still positively charged. Remember, positive, it can be like, it's sort of like a spectrum in a way. That's kind of how I like to think about the positive charge. Additionally, if you have something that is polar protic, so like you're increasing that hydroxide or OH minus concentration, or just having something that's like basic in the like solvent, then that also helps make that carbocation formation faster. Because if you have something that is negatively surrounding that positive charge, then that helps alleviate it because it can sort of form like proxy bonds in a way. So it can help support that positive charge, decreasing how positively charged it is. So it's decreasing its overall effect, making it seem more neutral. That's kind of all I want to talk about SN1. Then we have SN2, which is a one-step mechanism, which, as I said before, I don't know why. There's a lot of stuff in organic chemistry and just chemistry. Just anything that you'll send for MCAT in general, where it's just like, what were they thinking when they named some of this? And this is one of it. Since SN2, it's a one-step mechanism. Why isn't it SN1? I don't know. SN1 was probably discovered first. I have no idea. It is often referred to as a backside attack, which I always think is like really funny because I don't know. Um, Oh no, oh, I have it on here. Um, yeah, so because it's a concerted mechanism, so one-step mechanisms are often called concerted, it relies on two distinct elements, I guess. So you have the leaving group and then you have the nucleophile formation because it's a concerted mechanism. There is some intermediates, but they're not distinct steps by itself. So here we have our R group. And this shouldn't be tertiary. And most of these are typically secondary um carbocations just because it's like steric hindrance. And I'll explain it more in a little bit. So you have the base, it'll kick off that leaving group. That's kind of the difference is that there's no carbocation formation. It literally just replaces that leaving group straight off the bat. Out for blood right away. And then you have your base and your substrate instead of that leafing group. And leafing group is just kind of floating here. It's just there. It's just chilling in the solvent. And it's interesting because this always has opposite stereochemistry. So wedge to dash and vice versa. And this is because it, excuse me, the base, because it's like just right off the bat, like replacing the leaving group, it wants to it wants as least resistance as possible. So it's kind of think about it as like an assassin. The base is kind of like an assassin. It wants to be sneaky and silent. It doesn't want to set off any of the alarms, which would be like the steric hindrance. So those big chunky steric groups. That makes a lot of noise. It can set off the alarm pretty easily, so it wants to avoid those steric groups. And also the base itself, because it's an assassin, right? Assassins aren't clunky. They're typically pretty small too, right? So bases are in SN2, they're pretty small. Or nucleophile base. I don't know why I keep calling it a base. This should be nucleophile, but kind of there is slight differences. Sorry, my bad. If that was a little confusing. But nucleophiles, right? Like they're not they don't want to be like pretty chunky. Assassins are chunky, so the nucleophile itself will also be kind of small. And that is why it is a backside attack. So it doesn't set off that alarm, that trip, since it just right away will replace it, and it doesn't want to get in the leaving group's way as it pushes it out. Since if it were to attack from the front and the leaving group leaves from the front, and that's kind of confusing, right? Like there's a lot of like, oops, sorry, like I didn't mean to bump into you. Um, yeah. So that's kind of what I was saying. It prefers primary or tertiary substituted carbons. So this is a primary with the leaving group. This is a secondary with the leaving group. And then here I kind of have more of, I have the intermediates as well. So I have a leaving group that has a wedge, nucleophile that you're adding in, kind of has this proxy bonds, kind of in this intermediate state, the will they, won't they. Kind of think about it like a love triangle, right? Like kind of maybe the leaving group is like the small town, like best friend or whatever. And the nucleophile is like the rich guy, like rich new fling. I feel like in all those movies, it always goes for a rich guy, right? So it'll be the nucleophile will win that tug of war in the end. And as I was saying, because this was a wedge originally, this will now become a dash. Then it favors strong nucleophiles because remember, you're just pushing out the leaving group right away. This isn't a strong nucleophile for Sn1 isn't as much as a contributing factor. I mean, it's still nice, but remember, you're kind of more or less for like carbocations, so you're more dependent on the leaving group in carbocation formation. Whereas this one, you're kind of more dependent on the nucleophile pushing out the leaving group. Because remember, this depends on the leaving group and the nucleophile and the rates. Whereas this only depends on the leaving group and the carbocation formation. So the nucleophile itself is also really important as well as said leaving group and how stable it'll be. So what are some examples of good nucleophiles for Sn2? The smaller the better, remember, since they're assassins, right? Like they don't want to get in the way. They don't want to trip off any of the alarms in the form of those being like chunky, since it can like interfere with the steric groups on that carbon as well, where it's the leaving group is on, or just carbon, or just like steric groups surrounding the molecule. So OH minus, and also positively, I'm sorry, negatively charged too, just because that means that it has a lot of force. It's like highly reactive. It wants that partially positive carbon as much as possible. So you have OH minus, your amines, your R group with some metal. You could also have like some O minus here with some R group as well. Maybe forming an ester, you never know. And then with a good leaving group, those are kind of weak bases. And so like somewhat stable and unreactive. So if something is a weak base, and that means that it won't really have as strong as a negative charge as it leaves. So it doesn't have to compete with that nucleophile that you're adding onto the new the carbon that the leaving group was initially on, right? Up here, like you're not like really changing it too much. So it's not going to compete with that nucleophile. So like remember in this tug of war, right? This leaving group was more powerful than that nucleophile, then the nucleophile's not going to win that tug of war. Let's say the leaving group was that rich friend instead of the nucleophile. The leaving group's probably going to win, right? It has more power, more money. Um, yeah, and then it also like if something is like electron withdrawing, as well, it's easier to break the bond between the leaving group and that carbon. Because that makes sense, right? If you have something that is electron withdrawing, that means that it's kind of unstable. It's just like more partially positive as well, that carbon will be. Which makes it easy for a nucleophile to swoop in and kick off that leaving group. And something's electron withdrawing, it's kind of happy. It has its electrons and it's not gonna go after the carbon. Again, that is kind of all I wanted to say about Sn1 and Sn2 reactions. Hopefully that made sense. If it didn't, or if I made any egregious errors, please let me know in the comments. Once again, my name is Chacha. Hope you guys enjoyed.